Hi everyone, welcome back to my YouTube channel. Now we are going to discuss some topic about triangles and quadrilateral. So don't go anywhere, stay tuned.
Welcome to this explainer. Today, we're diving headfirst into the world of geometric shapes. Specifically, we're going to be talking about quadrilaterals, four-sided figures. But we're not just going to list them off. We're looking at them through a very specific, incredibly powerful lens that is going to completely change how you view geometry.
But before we get lost in the math weeds, I've got a bit of a mystery for you. What does an ancient Greek philosopher have to do with the shape of a kite? It seems like a totally random pairing, right? One is this abstract thinker from antiquity, and the other is a toy you fly on a windy day. But stick with me, because by the end of this explainer, you're going to see exactly how one simple, ancient theorem connects to the complex, everyday shapes all around us. Here is our roadmap for today. 1. Rectangles and squares. 2. The Pythagorean secret weapon. 3. Parallelograms and rhombuses. And 4. Kites and trapeziums. Let's jump right into section 1. Rectangles and squares. Think of these as our tutorial levels. These are shapes you're likely already super familiar with from everyday life, but we want to break down their structural DNA so we have a rock-solid foundation. It's actually really fascinating to define a rectangle not just as a static, boring box, but as a dynamic, rotated triangle. Just imagine taking a right-angled triangle, pinning it right at the exact midpoint of its longest side, the hypotenuse, and spinning it exactly 180 degrees. Boom! You've just mathematically traced out a perfect rectangle. It's a shape born entirely out of triangles.
Now this brings up the subtle but absolutely crucial difference between a rectangle and its much stricter cousin, the square. A rectangle is perfectly happy as long as its opposite sides are parallel and equal in length. The square, however, plays by a much tighter set of rules. It demands that opposite sides are parallel, sure, but all four sides must be exactly equal to each other. It requires absolute, perfect symmetry.
So you definitely want to have these foundational formulas firmly in your mental toolkit before we tackle the tougher problems. The rectangle relies on width and length, while the square's perfect symmetry makes its area and perimeter incredibly clean and intuitive.
Moving right along to section 2, the Pythagorean secret weapon. Because just when you think you've got this whole quadrilateral geometry thing figured out with those neat little straight boxes, we hit a roadblock, diagonal lines. And that means we need a serious upgrade to our toolkit. So enter our guide for this explainer, the ancient philosopher Pythagoras. I mean, first of all, check out that magnificent beard. But more importantly, let's realize the absolute genius he brought to mathematics. He's the historical figure who gives us the ultimate secret weapon for solving the mysteries of complex quadrilaterals.
Let's take a look at his exact words. In a right-angled triangle, the square of the hypotenuse side is equal to the sum of squares of the other two sides. Now, this famous quote isn't just some trivia to memorize for a history test. It's the master key. This is the exact tool that is going to unlock literally every single complex, skewed, and irregular shape we're about to face. All right, let's translate that ancient wisdom into a simple, incredibly powerful equation. The hypotenuse squared equals side 1 squared plus side 2 squared. Remember, the hypotenuse is always the longest side of that right triangle. This formula right here, this is our ultimate hunting tool for finding right triangles in every shape from here on out.
All right, section 3, parallelograms and rhombuses.
So let's see what happens when things lean a little sideways. Picture a parallelogram visually as a rectangle that's just been pushed slightly sideways by a really strong gust of wind. The opposite sides are still congruent, meaning they're equal in length, and they're still parallel. But because it's leaning, finding its area isn't as simple as just multiplying the outside edges anymore. To calculate the area of a parallelogram, which is base times height, you need the true vertical height, not that slanted side.
So how exactly do we find that true vertical height if all we have is the slanted edge? Well, step 1, we hunt for that right triangle hidden inside the shape. If you drop a vertical line straight down from the top corner, boom, there it is. Step 2, we plug the known slanted side, which is now acting as our hypotenuse, into the Pythagorean theorem. And finally, step 3, we solve for the missing height. By breaking it down like this, we can see exactly how Pythagoras helps us uncover those hidden measurements we desperately need for the area.
Now, just like the rectangle had a highly demanding cousin in the square, the parallelogram has a stricter version too, called the rhombus. In a standard parallelogram, the diagonals crisscross and cut each other in half. But in a rhombus, those diagonals are strictly perpendicular. They cross at exactly 90 degrees, forming 4 perfect right-angled triangles sitting right there inside. And all 4 outside edges are completely equal in length.
Here's your visual cheat sheet for these skewed shapes. For the parallelogram, the area is simply the base times that hidden height we just learned how to calculate. But check out how the rhombus area uniquely relies entirely on its 2 inner diagonals. Because of those perfect 90-degree internal intersections, you just multiply diagonal 1 by diagonal 2 and divide the whole thing by 2. It's a seriously elegant formula that's born right out of structural perfection.
And finally, Section 4, Kites and Trapeziums. We've officially made it to the boss level, the complex cousins of the quadrilateral family. This is where our secret weapon is going to be tested the most, but hey, we're ready for it. Let's look at the kite. It's formed by 2 different isosceles triangles squished together, sharing the exact same base. It's got a short top and a long bottom. But what makes the kite fascinating is that, just like the rhombus, its diagonals essentially slice it into 4 distinct right-angled triangles right down the middle. This means the interior of a kite is just perfectly primed for Pythagoras.
So let's break this down. If you need the outside perimeter, but you only have the measurements of those inside crossbars, what do? Well, you apply the Pythagorean theorem once to the top right triangle to find the short side hypotenuse. Then you apply it a second time to the bottom right triangle to find the long side hypotenuse. We literally use our secret weapon twice just to build out the perimeter. I mean, it's basically mathematical magic.
And that brings us to the ultimate grand finale shape, the trapezium. This is a highly irregular quadrilateral with a really unique set of structural rules. It has exactly 1 pair of parallel sides, usually the top and bottom. Its diagonals don't match up, and it can even shapeshift into a right-angled trapezium leaning on a flat side, or an isosceles trapezium balanced perfectly like the base of a pyramid. So, how in the world do we conquer the area of this thing? You guessed it. Once again, we hunt for the right triangle. Step 1, drop a vertical line right down the edge. Step 2, use your Pythagorean theorem with the slanted side to find that vital vertical height. And step 3, plug that height into the grand formula, multiplying it by the average of the 2 parallel sides.
All right, this is your final structural roadmap. The kite generously shares the same diagonal-based area formula as the rhombus, while the trapezium demands its own unique equation. Understanding exactly how to find the missing variables for these formulas using right triangles, that is the ultimate proof that you've mastered the absolute most complex quadrilaterals out there.
So, with this secret weapon securely in your back pocket, I'm going to leave you with a challenge. Now that you have the Pythagorean tool, what complex shapes in the real world can you deconstruct? Because honestly, every bridge truss, every sloping roof, every kite flying in the sky, they are all just hiding right-angled triangles waiting for you to solve them. Keep looking for those hidden angles, keep applying that structure, and I'll catch you in the next explainer.